Welcome back. In the last video, we talked about some of the components of a production machine learning system. We talked about the three main stages of the machine learning pipeline, which are the data ingest stage, the model build stage, and the model serve stage. In this article, I want to share more insights on how to effectively deploy your ML models and some of the foot guns and snares you have to be wary of when deploying these models and ensuring that they continue to operate how you intend them to operate. So let's dive right in. As I said in the last article, we discussed the components of a production grade machine learning pipeline. While having a robust machine learning pipeline is a major step in the direction of success, it's equally important to know how and when to use this pipeline to avoid common issues like model staleness. In this article, we're going to discuss two critical decisions to be considered when architecting an ML system: training design decisions and inference design decisions. While an email spam detection system will benefit from dynamic training and dynamic inference, a sales revenue prediction service would employ dynamic training at intervals and static inference. Let's try and understand what these terms mean and for what use cases we might want to apply different strategies. Training design decisions. What's the difference between physics and fashion? I'll give you a second. Well, the answer is that physics is constant and universal, whereas fashion is constantly changing. So, how does this relate to ML models? If the relationship you're trying to model is one that's constant, so like physics, then a statically trained model may be sufficient. However, if the relationship you're trying to model is one that is frequently changing, like fashion, then a dynamically trained model may be more appropriate. So, what is static training and what is dynamic training? Well, they're essentially the same, except with dynamic training, we repeat the loop over and over again. So, this is the ML pipeline which we discussed in the last article. And for static training, we just use that pipeline once and we're done. Whereas for dynamic training, we run the pipeline and we take the observations from the model serve stage and we use that as feedback for the data ingest stage. So we're constantly re-evaluating and possibly retraining the model. A static model is trained offline. That is, when we train the model exactly once, and then we use that trained model for a while. A dynamic model is trained online. That is, data is continually entering the system, and we're incorporating that data into the model through continuous retraining. So this could also be, a use case for real-time data. For a model that's taking in real-time data and learning from that data, you would want to train the model recurrently, right? So that would be an example of dynamic training. Static training is simpler to test and build because you only have to do it once, but it's likely to become stale, and it probably won't adapt to changes in the environment. Dynamic training is harder to build and test, and it's also more expensive because you have to retrain the model, but it will adapt to changes. Let's go through some examples and see which training style we would use for each of these scenarios. The first scenario is predicting whether email is spam, and the training style we would want to use is dynamic. This is because spammers will probably discover ways of surpassing whatever filters you impose within a short time. So your environment is constantly changing. In other words, spammers are constantly developing new tactics um, to override these spam filters. So dynamic training is likely to be more effective over time. The next scenario is Android voice text. And for this problem, we might want to choose between static and dynamic training. For a global model, training a static model offline is probably fine. But if we want to personalize the voice recognition, we may want to do some training online, on the phone. The next scenario is shopping ad conversion rate. And for this, we would prefer a dynamic training style. And the reason for this is that conversions may come in very late. So I might be shopping for a car online, but I might only purchase that car, for a very long time, maybe months into the future. So this system could use dynamic training and then regularly go back at different intervals to catch up on new conversion data that has arrived from the past. So if we were trying to predict the conversion rate for this particular system, we would want to catch up on data that has arrived from the past, and we would want to update the model and retrain it based on that new data. But we might want to start with static training because it's simpler and easier to test. So how do we choose between static and dynamic training? Again, the thing you should remember is physics versus fashion. If the relationship you're trying to model doesn't change frequently, such as facial recognition, then static training is probably sufficient. However, if the relationship you're trying to model is constantly changing, such as trying to detect diseases or e-commerce websites, then to avoid model staleness, you should opt for dynamic training. So that was training decisions. Let's talk about serving and inference design decisions. When deciding on a serving architecture, one of our goals is to minimize average latency or inference speed. We don't want to be bottlenecked by slow to decide models. Okay, static versus dynamic serving. In static or offline serving, we make all possible predictions in a batch. We write these predictions to a table, and then we feed these to a cache or a lookup table. So basically, we take all possible inputs, feed them to the model, and generate all possible outputs, and we just store that in a table so we can reference them later. In dynamic or online serving, we predict on demand using a server. Static serving and dynamic serving follow a space-time trade-off. In static serving, the workload is space intensive because we have to store all those predictions. And it's going to be higher storage cost, but we'll get low fixed latency. And there's also lower maintenance. For dynamic serving, it's compute intensive because for every request, we need to process the request, run the model, and then send that request back to the client. There is lower storage cost, but the latency isn't fixed. Depending on the model architecture, depending on network speed, there might be a variable latency, and you can get very high latency if you don't configure the right parameters. And there's also higher maintenance because you also have to deal with the servers, load balancing, and things like that. So the choice between static and dynamic serving should consider factors such as latency, storage and CPU costs, and the nature of the problem. However, the relative importance of these considerations can be difficult to assess. Therefore, it might be useful to view this trade-off through a different lens, through peakness and cardinality. Peakness refers to how concentrated the distribution of the prediction of workload is. This is similar to the definition of peakness in relation to data, where peakness in a data distribution is the degree to which data values are concentrated around the mean. A real-world example of this is a model which predicts the next word based on the current word, which is used in the autocorrect feature of mobile phones. And this could be highly peaked because a small number of words account for the majority of words used. Cardinality, on the other hand, refers to the number of values in a set. In this case, the set is composed of all possible things we may need to make predictions for, aka the set of all input values. A model predicting sales revenue given organization division number, let's say there are 6 divisions, has low cardinality. That's because there are only 6 possible inputs to the model. Therefore, it's very low cardinality. A model predicting lifetime value, on the other hand, given a user for an e-commerce platform, has high cardinality because the number of users, the number of characteristics of the user would be fairly large. So together, peakness and cardinality create a space. And analyzing the space, we can inform our decision on whether to use static or dynamic serving. Area 1 represents when cardinality is sufficiently low, such as when predicting sales revenue given organization division number. So that's this blue region right here. When the cardinality is low, we can store the entire expected prediction workload in a table and use static serving. Area 2 represents when cardinality is high and the workload is not very peaked. So that's this yellow region right here. An example of this is a general image classification model, as there are many possible images and they're fairly distributed. Now, in practice though, a hybrid of static and dynamic serving is often chosen. And for area 3, where the cardinality is high and the peakness is also high, we might want to opt for this hybrid approach. So models that fall into area 3, where there is sufficiently high peakness and cardinality, benefit the most from a hybrid approach. An example of this is an e-commerce recommendation system, where the recommendations for the most frequently buying users can be statically cached, while the recommendations for the rest of the users are computed on demand using a server. I think it would be useful to go through a case study to understand what are the kind of questions we want to ask and how we will decide whether to use static or dynamic training and static or dynamic serving. So in this example, we're going to expand on the e-commerce recommendation system we briefly touched on. For training, the question we want to ask is, what drives an e-commerce recommendation system? Well, it's customer preferences, right? Because as customer preferences change, the recommendations should also change in line with those ever-evolving customer preferences. So, is the relationship more like physics or fashion? Well, in this case, it would be more like fashion, right? Because customer preferences are changing over time. Therefore, a recommendation system will definitely benefit from dynamic training, so that recommendations do not become stale over time. Serving. Now, how do we decide how to serve this model? A purely static approach would mean that we calculate the recommendations for each user and then store them in a lookup table. But for a site with millions of users, this is simply unfeasible due to the enormous compute and storage requirements for that table. On the other hand, a pure dynamic serving approach may have high latency, leading to dissatisfied customers. In this case, it makes sense to use a hybrid serving approach. The first step would be to identify the power users of our application and pre-compute their recommendations. These users would likely benefit from more prompt product recommendations, as they are more frequently using our product. So for these customers, we want to prioritize low latency. For the rest of the users, the recommendations can be computed on demand via a server, API, or microservice. For general recommendations, such as Christmas sales, a static serving approach for all customers will probably make sense as well. That was all for this article. I hope you gained something valuable. Hope you learned a little bit more about how these production ML systems are working. And, I'm just sharing content which I'm learning online and just sharing it with you all just to benefit the machine learning and data science community. So I hope you got something valuable out of this. And if you did, smash that like button and definitely hit that subscribe button to make sure you get updated on my future videos. That'll be it for now, and I'll see you in the next video. Peace. That'll be it for now, and I will see you on the next video. Cheers. That'll be it for now, and I'll see you next time. That'll be it for now, and I'll see you next time.